Hey students, welcome back. It is Monday, February 6, 2023, and this is Mr. Ross, and I want to let you know the lessons about today. Our mission today is learn about logarithms and how they relate to exponential equations. So before I start, first think about all the things that you know about inverse functions that we learned in the first semester. All right, so just jot down any ideas, thoughts, vocabulary, phrases, pictures, notations you remember when you first talk about inverse functions back in the fall. So I'm gonna give you about a minute to think about it. So pause the video and then come back. So right now, pause it. All right, hopefully you thought about it. And hopefully you thought inverse functions had something to do with, say I gave you y equals 2x plus 5. The inverse, you would switch x and y, and you would put x equals to 2y plus 5. And then you saw that for the letter y. Y is over here now. 2y plus 5. You subtract 5 from both sides. You get x subtract 5 equals to 2y. You divide by 2 on both sides. So you get x subtract 5 over 2 equals to y. And remember, I always told you to put a little inverse sign on it to just remind you there was an inverse. That was one way we can look at inverses algebraically. On a graph of our inverse functions, you should remember that one of the graphs could look like, right, first of all, the symmetric about the line y equals x. So one graph may look like this, and the inverse function has this mirror image about that y equals x. So that's one way to tell if inverses by looking at the graphs, if they're mirror images reflective of the line y equals x. And the last thing was if you can stick one into the other, as in you took this function, replaced it in for x, if your output was x, and vice versa, you should have gotten, they should be inverses. So basically, if I took x subtract 5 over 2 and placed it right here, they should be inverses. So it would be y equals to 2 times x subtract 5 over 2 plus 5. And then if you multiply this together, we should see that the 2 is going to cancel. You can get x subtract 5 plus 5. And then if you add that, you should see that the 5s here cancel. And you just get x. You get y equals x. So that's a good sign as an inverse. You don't know for certain until you switch the other one back into it, to this equation. And anyway, so you switch them both and they both get x. Then they're inverses. But that's what you learned already. Now, logarithms are inverse of exponential functions. For example, this is the function that we would have talked about in our last quiz, like a basic y equals 2 to the x exponential function. Its inverse is log base 2 of x. Notice how it says f to the negative 1 means, that little negative 1 means inverse. All right, so if you wanted to check it, here it is. I like to see them on the same screen so I can see if they truly are symmetric about the line y equals x. So I'm going to take both of those functions right now and plot them in Desmos to see if they look symmetric about the line y equals x. So in Desmos, I'm typing in y equals 2 raised to the x power. And the second equation is going to be y equals log. So it's under functions here. You can go down to probably calculus section. There it is. You got log. You want log with a different base. So here it is. So the base we wanted was 2. And we're going to put base 2 to the x of x. So if you look at that, they look like they might be symmetric about the line y equals x. So just to see, I'm going to write y equals x here. If I take a look at that, that looks like a perfect mirror image about the line y equals x. That's enough for me to know it's inverses. If the mirror image is about the line y equals x, then they are inverses of each other. So I know these two are inverses. So my mission for you is two things. First thing is this. Notice how this x column, the numbers are 2, negative 2, negative 1, 0, 1, 2, 3. But then in the y column for the inverse, these numbers appear negative 2, negative 1, 0, 1, 2, 3. And then in the x for the y column in the original function, 1/4, 1/2, 1, 2, 4, 8. Goes to the X column, 1/4, 1/2, 1, 2, 4, 8. Notice how they switch values. So if you know the original values, you get the inverse, you can just switch to X and switch to Y in different columns. So just keep that in mind. So just to help you out a bit, my mission is, well, before I give you the mission, quick review. If I gave you y equals 2 to the x, we know the asymptote is y equals 0. We know domain is all real numbers because it doesn't start going to the left or right. We know the range is all real numbers greater than 0. You might write it like this, 0 to infinity. This person wrote it as an inequality. Y is greater than or equal to 0. And you know what? I shouldn't include 0 because it doesn't actually get there. And the y-intercept is right here. It's at 1 for the original function. And the x-intercept should be 0, 1. This is actually written wrong. Whoever did that wrote them backwards. So the y-intercept is actually 0, 1 because that's a coordinate over 0, up 1. So they made a mistake. It happens. Moving on. So anyway, so that's the original function. And then this is the inverse function. And we got a different asymptote. So in our inverse function, instead of it being y equals 0, it's now x equals 0. So that's been switched. Instead of my domain being all real numbers, my range is now all real numbers. I use a symbol for all real numbers. Instead of my range being y is greater than 0, I'm changing that y to x. My domain is now x is greater than 0. My x-intercept now is here, which is at 1, 0. And my y-intercept is now none. So everything switched places. So just notice that. All right, so other key features are where increase and decreases at. So if you notice in the original function, it increases from negative infinity to positive infinity. It never decreases because it's always going up. As you go from left to right, each point is higher than the last. My end behavior is as the function goes to positive infinity. The curve approaches positive infinity, and it does. As you go to the right, curve goes up. And then as it goes towards negative infinity, the curve goes towards this number here, which is 0. So all that's true. And when we inverse it, everything should be kind of changed. It increases now still. It's always higher than the previous. So it's still negative infinity, positive infinity. So I take it back. Everything didn't change because that didn't change. It still does not have a decreasing interval. And the end behavior in this case now, as x approaches infinity, so we'll go this direction, the graph still goes up. So I'll go this direction, I have to go up, touch the graph, so it still goes to infinity. And when I go to negative infinity, well, this graph didn't really go towards negative infinity. It has a wall here at that axis. So I'm going to say when x approaches 0, y approaches negative infinity. All right, now let's get practice. I have a page for you I'm going to give you now that deals with graphing logs of these different bases. So you're going to graph them in Desmos. You can create a table with those numbers. After you get done, you're going to do this last activity here on the bottom where you have to match these equations with the proper inverses. You can do that all with Desmos. All right, so that's your mission. To go next, get this practice from the graphing logs base 10 and 1/2 in E using Desmos and using the table of values and then the matching activity. That's all I have. Good luck.